All right. I'm Andrew Thompson. We're going to be starting off with the last problem, of course. So this problem gave us the maximum stress allowable, and we're trying to find the cross-sectional height of this beam. So here we can see it's subjected to two loads, and it's uneven. So obviously, in order to find the unknowns, dy, ay, there's not going to be any ax component because there's no horizontal x loading. You just do a moment and then a total forces in the y direction. We're only going to go over that. I feel like we've been doing this for like 10 months now, however long. So it's pretty intuitive. You're going to get your dy reaction is 3 kilonewtons and your ay is 2.4. Again, you can see that those are uneven because right here there's a heavier applied force of 3.6 versus 1.8. And then using these values, we can go ahead and create our shear stress diagram and our moment diagram. So first we start out with an applied AY of 2.4, and then we go down 1.8, and then we go down again 3.6, and then back up to 3. So at 0. And from this diagram, we can see that our maximum moment is going to occur right here at 1.6 meters from point A. So that would be right here. And then we can create our moment diagram. Pretty simple, just using the area under the curve, blah, blah, blah. You know how to do that. So that's going to give us a maximum moment of 2.4 kilonewton meters, excuse me. And then, since we're trying to find out this cross-section, we can go ahead and use the selfish formula, the negative Mae over I. So plugging in our maximum moment here, and now we're going to go ahead and look, since our neutral axis is going to be right in between this, since it's a nice little rectangle, we don't need to solve for the neutral axis, which is really great, we love that. So your y is just going to equal h over 2, so pretty simple. And then for your moment of inertia, that's just a simple 1/12 base height cubed, and of course our h is going to be in factors of unknown. And then you can just go ahead and isolate, pretty simple. You're going to get 0.181 meters. So that's a pretty simple problem. Yeah. I think it's just combining a lot of different concepts that we've learned and then doing it in reverse, because now we're solving for the height rather than solving for this maximum.
I think you can still do it. Can you do it using S at all?
Yeah, so S is equal to y over I. So I think you would get like 1/6 base height squared. Instead of, so if you flipped this to the bottom, it'd be a 6.
Oh, so it'd be the same exact thing.
Yeah, so
I think that's the method I used.
Yeah, I think this is more intuitive for me because you're only memorizing this equation, like you don't have to memorize the other equation. Less variables. Yeah. And then this also explains where that is derived from. You can see where the 1/6 base height squared comes from. But yes, good question. Any other questions?
I have a question about, I've been wondering these about the moment graphs.
Yeah.
Do they always start and end at 0?
Not necessarily. That just depends how your moment works. Like if we had an applied moment, this is all theoretical by the way, but if we had something like right here, might not necessarily end at 0. I feel like the ones we have been doing have always started and ended at 0.
That's what I'm wondering. Would they always start at 0? So that means at the end
No,
would change.
also. So let's say this applied moment was at A, just like this, you would start over here.
Oh, so it's like a
here.
reaction. It's like
Yeah, you could say that. So
how a reaction force would make that go.
Yeah, so here we didn't start at 0 because there's an initial force at AY. So it's all depending on the perspective that you look at it, but yeah.
Even if it's a static equilibrium, should it not always...
I think you're right. I was just thinking about that. Yeah, so I think it would always start, or end at 0. End at 0, yes. Yes. Yeah, because otherwise we couldn't use the total forces in the y direction to solve if we're setting this equal to 0, so that's going to imply that we're going to end at 0 here. So, yeah. Good question. Shall we move on?
Yeah, cool.
Thank you.
Yeah. You might need to scoot that back a little bit. I don't know if you can see everything.
We can just move it down more and more. Yeah, we'll just do that. Okay, so this is number 1. We are trying to find the maximum tensile and compressive forces acting on here. And so I didn't put they're all 10 by 5 millimeters. So all the areas are going to be equal. We start this one. We're ultimately trying to get everything to plug into, you call it the selfish equation?
That's what she called it.
Okay, well, I'll call it that. That's easier to say. So we're trying to find everything so that we can solve the selfish equation. So we start with the centroid because that's the denominator. We need the moment of inertia, which you need the centroid for. So fill out the chart. This is like 30A stuff. I don't really need to go over it. In the end, we'll get that y bar is equal to 0.025. And the way you can think of that is like 0.025 will be like the neutral axis. I don't know how the axes work. I'm gonna call it that. The neutral. So like this is 0.025.
Or the global centroid.
Is that what we call it? The global centroid? Yeah. Okay, sorry. So the global centroid is 0.025. You can go down to here, which is going to be, we'll call this 0. Sorry, we'll call that 0. And this is negative 0.025. And then up here, because this whole height is 5 millimeters? 6 millimeters. Sorry. So this would be upwards 0.035.
So the 0.025 is your neutral axis, correct?
Yeah, but I'm going to call it 0 because it makes more sense in my head.
Yeah, because the y in the selfish equation is the distance
It's like,
from the axis.
So it's like up the 0.025.
How come you use those values?
What values?
Well, like how come you do it right here instead of like right here? You know what I mean?
Right here instead of right here.
Like at the very end versus in the middle.
That's just the way I learned it, I think. I don't know. Isn't that the way it works?
No, yeah, that is the way it works. But okay.
I wouldn't
I'll
be
just
able
answer my own question. Okay, but so the neutral axis is where it experiences no tension or compression, right? Because it's at equilibrium, because of the way the bending moment's working. So as soon as you go over here, the forces are. So if it's bending like this, right? This force is going to go like this, but then as soon as we cross over here, it's being compressed, right? So like think about if you're bending this, your skin is bunching up versus here it's stretching out. So the maximum, since we're looking for that, is always going to be at the bottom because that's experiencing the most, right? So the further away you get, the more tension or compression.
Makes sense.
Yeah, so that's why you're using the largest value, I guess, if that makes sense. But yeah.
See, I just got him to answer his own question. It's a good way to learn. So yeah, we have, I got the equation over here with the parallel axis theorem to find the moment of inertia. So we plug that in. I didn't want to write it all out here. It's a long formula. We'll get 5.12 times 10 to the negative 7. So now we have our denominator. We already have y, which was our global centroid. And now we need the maximum moment. And I wanted to use the previous example. Basically, we got 1200 for it. You'd find it the same way as here. It's just like the maximum value that you'd find. It's pretty easy. You get that by your free body diagram at the top up here, and then you make your diagrams.
Using the given.
Yeah. So you would do your shear diagram, then you'd use the areas of this.
Yes.
To get the moment diagram, and then you use the moment diagram to get the max moment.
So true.
It's like it's like a ladder.
That. Yeah.
So with that, you have everything to plug in. This way conceptually makes sense. So this is multiplied by a negative, and tensile forces are positive, compressive forces are negative. So in order to get the tensile force, we need to use a negative global centroid value so that the negatives cancel out and we get a positive. So we're going to take this distance up here, the negative 0.025, and plug that in, and then you get 58.6 times 10 to the 6 megapascals. And then for the compressive, we'll use the positive global centroid value, which was 0.035. Plug it in all over again. You'll get negative 82 times 10 to the 6 megapascals, and that's the compressive force.
So for both of these, our moment of inertia is the same. It's our net moment of inertia.
This is the same for both, yeah.
Yeah.
Same that. The only thing changing is like whether you go up or down.
Oh, got it.
Yeah. And then the idea is that you need to make these cancel to get a positive, so you go negative. Compressive is a negative value, so you don't want to cancel it out. So you go with the positive value.
Okay.
Oh, okay.
Thank you.
Should we flip it?
I'm Thomas Brandt. This is number 2. Try to fix the glare here. So we're given this this diagram here.
The cantilever beam, right?
This one is not a cantilever.
Oh, this is not a cantilever beam. It's just a beam.
It's just a beam.
Okay, yeah, you're right.
And also, unlike a lot of equations, a lot of beams we get in this class, these points are not applied at the end, which will be important in a second here. Basically, this was a multiple choice question about you had to pick the correct shear force diagram, and to do that, first I create a free body diagram and try to make sure we account for all our forces here. So we're given the distributed load. One thing we need to add ourselves is the normal forces due to the points right here. There's one right here for Cy. C will also have a Cx, but we'll find that doesn't matter here, and it will cancel itself because it's on a roller. This will have a dy. That was bad, but if you notice, the distributed load begins before the normal force upward is applied. So in our diagram here, this is the correct one. We begin a downward slope because of our distributed load downwards. And then this jumps up because of our normal force. And you can calculate the normal force using net force equations, and then you can find what these values would be. We didn't have to do that for this problem, but you do for some of the other ones. Now we're here. This is at point C. We just jumped up. Now we're going to continue our downward slope with the distributed load until we hit the point of normal force on D, in which case we'll jump up again, whatever the value of dy is. And then because this normal force is applied before the end of the beam and before the distributed load is done, we'll continue the downward slope of the distributed load. And Evan asked about this earlier, but yeah, you'll also see that this is beginning and ending at 0. It's ending at 0 because we're at static equilibrium. Yeah, I think that's everything. This was pretty straightforward. And concepts you'll apply throughout all these problems.
I guess I'll build off of that. I'm doing number 3. It builds off of this because you did the shear force. I'm doing the bending moment. So the first part just asks for the correct bending moment diagram. And using this diagram, we can just see that the integral of like these lines. So this is a linear negative slope. This will be a negative parabola. So we start with a negative parabola, and we jump up and also still continue to be in a negative slope to linear whatever. So we still have a negative parabola, and it continues to that. So every single line here is actually a negative parabola. It's just the integral of this line, you could say. And then it asks for the maximum normal stress. So our normal stress, we're given that is m over s, and it actually gives us s. So the only thing we need to do is just find m. So we know that the maximum m here, it gives it to us that it's at 6.75. So if we cut it there at that moment, you can either take left or right. I just chose to take the left side. So if we cut this...
So they'd both give you the same answer?
Yeah, they should. At 6.75, I'll just make a cut here. So we have the Cy force, and we have the downwards load.
Distributed load.
Yeah, distributed load, yeah. So we're going to account for both of those in the moment. So for distributed load, actually, we learned that like the V equation, whatever our load is m is just the integral of that. So our V is px, or wx, I guess I should say, where w is our p load. So the integral of that is going to be 1/2 p, which was 10 for me, and then x squared, where x is our L. So where I cut it, if we start at the cut and move over to the other side, it should be 6.75, what was that, meters or millimeters? So that'll be our x. So we could just plug that in. So that's our moment for the load, and then we just take a normal moment for the Cy force. So it's just a Cy times the distance. Since we know that the cut is at 6.75 and the distance from A to C is 2, we can just say that C to the cut is 4.75. So that'll be our distance. So we just subtract the 2 and get our total or a max moment. Oh, that shouldn't be 45. We get our maximum moment, and then to find the answer, we just take our maximum moment and divide by s, which is what it gives us. And I got 45 KSI.
Thank you.
Pretty straightforward.
Any other questions?
I think that's it.
Thank you.